My name is Armin West. I'm on the science staff here at the Space Telescope. And I just want to give you, as a preparation, just a very quick presentation about, give you an astrometry primer, what are the different things that you have to know. And then after that, we will go over some of the WCS alignment principles and do then some JHAT example notebooks. So just a very quick astrometry primer. As you know, so we have a sphere. It's a spherical sphere, and so it's not a flat area, and that of course gives you issues. So that is solved by basically when you have an image to project it into a tangential plane. So in this on the right side you see this celestial sphere, and this red little square illustrates a field of view of JWST instruments. So the detector is a plane, and it's a very small area, but the sky coordinates are spherical, and so you approximate that with a tangential plane. And so now let's go through very quickly how this actually works. This tangential plane is the simplest ideal case. So on the right you see an illustration of a detector, and normally you have the coordinate system of the detector at the lower left corner in XY coordinates. And in this, the simplest case, the detector is actually aligned with the y-axis, positive y-axis to the north and negative x-axis to the east. So what you normally have is when you have a detector, you have what we call a pixel scale, P, and that tells you how many arc seconds per pixel you have. Typical pixel scale for HST and JWST goes from 0.03 arc seconds up to 0.1 arc seconds. Ground-based detectors usually have between 0.2 and 1 or even 2 arc seconds pixels. So how do we get from XY to y descension declination? In this, the simplest case, so first thing we want to do is we want to convert the XY coordinates to an XY coordinate system that is centered in the center of the detector. So this is just like a simple shift. We subtract x0 and y0, where x0 and y0 are the coordinates of the center of the chip. And then we have to go from the pixel scale to basically degrees. And this is a scaling that you see here. So this gives us, this gets us from delta x and delta y to delta ra and dec in degrees. And then we just shift it to ra naught and dec naught, where this ra naught and dec naught is a coordinate in the center. So this is just an illustration how to go from xy to ra dec internally when we do the WCS. Of course, the real world is not quite as easy. When I said that, the detector has like this pixels that have the same area and length, that's unfortunately not true, because we have these optical effects by the telescopes, the camera, all of these different things. They are not perfect, and that means that when we actually look at an image, a detector image, in reality it's actually distorted. Lots of times it has to first order such a pincushion distortion that looks like that. This is just like a typical distortion caused by the camera lenses. And so you have also second and third order effects. So there can be symmetric and asymmetric distortions. So the idea is that when you have this X and Y positions that you measure with photometry of your stars, you then want to basically undistort them, and you do this in the most general way with polynomials. That's a SIP convention. And so basically what you're doing is you're taking this distorted XY coordinate system and transform it into an ideal coordinate system for which each pixel is has the same side lengths in the same area. So this here is now the real world WCS Primer. So you start with X and Y, then you move it to the center of the detector, and then you use these distortion terms that are normally provided by the observatory that are measured with calibration frames. And so you use these distortion terms that you don't have to worry about to determine, and you can just convert that into this ideal coordinate system. Then you use a rotation matrix that rotates it and also scales it to go to delta Ra and delta dec, and then you just like add that to your central position. So this is like the general way how you do that. So how is this presented? In general, so WCS is in the fit header, and I want to say something about that later on that is specific to JWeb. But in general, the WCS in the fit header, and it's encoded into this CRPix12 and CRVAL12. This is your most generic thing. It basically tells you that it's a pixel value CRPix12. You have the right ascension declination that is in these values. So that's your anchor point. And then you have the rotation matrix in these CD values here. And that just goes from the delta X, delta Y to delta Ra and delta dec. In this case, the C-type 1 and 2 define what kind of tangential plane system it is. And you can see it has the zip ending. And that means that in the rest of the header, there's also these polynomial coefficient that do the distortions. So when we do a WCS alignment, what are we doing? We go from XY to the ideal coordinate system. That's always the same for each image. We can do this right away without having to do any work. But then for each image, what we have to fit is rotation, scale, and the offset to the right ascending declination. How do we do that? We match a reference Ra dec to an XY, and this is what is actually the difficult part. Because in order to match, we have to have some kind of idea where this image is on the sky. And that comes from the telemetry of the JWeb Space Telescope, or from the telemetry of your ground-based observatory. So you kind of guess the 6 parameters that we use to do the rotation and the shift, and you use this guess to kind of like have this guess of the Ra dec, and then you match that to the reference catalog. And that is actually what is the most difficult part. To get this matching done, to get the right matches, that is the art that you have to do. Then to fit the rotation and the shift, that is just like a simple, Python routine and really easy. And so this is what we basically JHAT we did to do exactly that task, to take an input image, get some photometry, guesstimate what kind of right ascension declination it is, and there we can be off in shift and rotation, try to match it, and then identify the good matches. And that's what today's session is all about.